like we're just about there. Welcome back, everyone. They discourage us from starting early, but we're towards the end of the semester, so what the heck? Let's start just a bit early today. So today we're going to be in section 6.3. I'm not going to try to do a lot of problems in that section since at this point it's a good idea to start converting over to reviewing for the course. So I do have a couple of problems there that we'll be taking a look at where really the theme is just to look at some old integration techniques. I have a U substitution in there, and also we'll look at using R6, estimating something using approximating rectangles at right endpoints. So we'll do a few review problems there. Sorry, talking's hard. Then we'll go over to this review document next. Any questions at all, folks, before we get started? Okay, and one thing I should ask before I get started with any of these things, if you have questions you want to take a look at during the review, whether they're, say, old exam questions, homework questions, anything at all, I'll be happy to do that, to include it in the review. So this document here is just in case we run out of questions from the class. So you're highly encouraged to bring some. Otherwise, we'll be going through those topics there. We won't try to complete every problem in that review document. It is kind of large. The solutions are at the very end, but we'll try to pick out ones that seem like they'll probably be good and interesting, real final exam type questions. Well, that's my whole spiel for the announcements today. Any questions at all, folks, before we get started? Okay, well, let's look at this new method of cylindrical shells. Maybe before we get started, it's good to compare the two different methods. Sometimes our author refers this to the method of slicing. Kind of makes sense. We're using cross sections. If we can find an actual formula for the cross section as x varies from A to B, then the area of that three-dimensional structure is just this right here. Sometimes this can be a really clever way to find the area of something, but you might have noticed we're not trying to do some of those advanced problems. Most of the problems were just rotate something about an x-axis so we can find an area, and this is where the method really shines. So for this method, rotation about x-axis is great. If you rotate about the y-axis, you might make it work, but sometimes the curves are just not going to be nice to play with. Or maybe the curves are so bad, even if you rotate about the x-axis, we need to change our method. That's where 6.3 comes into play. Instead of trying to find the cross sections, we're going to take something that is definitely going to be rotated this time. So this is a very specific method. It's not as general. But if you rotate it about the y-axis, this region here turns into some weird looking solid. And we're going to use these cylindrical shells. Our author did some derivations to find the volume of it, to calculate the volume of this thing. How it works is we partition from A all the way to B in different subintervals of equal width, delta x. Pretty much we're just going right through our problems of chapter 5. So here's our partition here. We get all these different rectangles, just like we did in chapter 5. The new thing is these are going to be now rotated. And every single one of these is now a cylindrical shell that looks about like this. But we can calculate the volume of every single one of those cylindrical shells. It would look like this thing. And that's not terrible, except if you want to get an accurate estimation on volume, you need more and more of these approximating rectangles. This is 5 of them. You need more like 500, depending on how accurate you want your answer to be. Now, if you want the dead-on exact volume, this Riemann sum is not good enough. We have to take the limit of the Riemann sum. And the moment you take a limit of Riemann sum, that thing converts into the definite integral. We have xi bar, f of xi bar, converting to x, f of x. And the delta x, which was just the width of the shell, is now a symbol, dx, reminding us what to integrate with respect to. So this is our full formula, and this is how our author encourages us to think about it. It's a great way to conceptualize the formula. This 2 pi r is really just a circumference in a certain sense. The r is the shell radius. So over here, it'd be the distance from this point all the way to the center here on the x-axis. H of x is going to be the shell height. So it'll be the distance from the bottom to the top. And that's the whole procedure. If you can come up with the radius and come up with the height from a diagram like this, you're in really great shape. Any questions, folks, before we try this out? Okay, so that's our new procedure to take a look at. And we took a look at this document before we closed out class on Wednesday. This is the same function that we saw in section 6.6.2 altogether, but now the rotation is different. We're going about the y-axis. If you rotate that whole thing about the y-axis, that's going to look like some kind of weird, not great function in bold, maybe a fruit bowl or something like that, using a lot of mass. But here's a different diagram to take a look at. X right here would be one of those locations where we go from 0 to 4, the valid interval of integration. And this band right here would have been just one cylindrical shell coming from there. So what we need is this distance, that's the shell radius. And the problems that we're doing, the shell radius is pretty much just always going to be the variable. That's because we're rotating about the y-axis. And there are other weird problems where maybe you're rotating about 4, but we're not going to have time to get to some of those other problems. You might see them in the reading as well. So for pretty much all the problems that we have time to get through, the shell radius, which is, let's match that color coding, r of x, is just going to be x in these kinds of problems. It's the distance going from here to here. Does that make sense so far, folks, for the radius? Okay, then the height of the shell, we can see it down here where it's visualized a little bit better. But the punchline is, it's just going to be the function itself that's giving you the height in this particular diagram. So the shell height, which we call h of x, is just the function itself, square root x. So with those two pieces of information, we're ready now to get the full exact volume of this thing when it's rotated about the y-axis. See if I can zoom in just a touch more. We'll just use this formula right above. Any questions or comments, folks, before we start this integration? Okay, this one's not too bad as an integration, but this kind of integration problem could be on the final exam. It could be volume equals, we're integrating from 0 to 4. Those are the valid choices of x in this diagram. A 2 pi comes into play. That's conveyed from the rotation that we're doing right here. Now throw in the radius, which is just x. Throw in the height, which is square root of x. Let's do one better and put in x power 1/2. And that's our integration problem right here. So again, this on its own is a valid final exam problem that we could encounter potentially. And so think of this as a weird process to practice more integration. That's our main punchline for chapter 6, really. Once we get here, if we're going to find an antiderivative, we don't like a function multiplying a function. If it was a constant like 2 pi multiplying x and nothing else, we'd be in good shape. But if you can find a way to simplify, you always want to. We have two base x's multiplying. Let's consolidate into the base x written once. You can also kick out 2 pi if you don't want it there. Let's do that. 2 pi is outside now. Integrate from 0 to 4. And this x has a power of 2 over 2. Add those up, and we are now at power 1/3. Or let me try again. I was almost there. That looks like 3 halves, right? 3 halves. Just a moment there, I forgot how to do fractions, but we're back. It's a power 3 halves. So now with that, we can find an antiderivative really much more streamlined. Let's go 2 pi, a little bit of space, put in x. And anyone see what the new power should be on this x? Exactly. We'll add 2 over 2. That's adding 1 to the old exponent. So now 5 over 2, which means we should multiply by 2 over 5, the reciprocal. So there's our 2/5. Bunch of constants all just settling right here. Yes, go ahead.
I'm just pulling up the x power 1, x power 1/2, and that's 3.
Oh, this right here?
Yeah.
That came from the square root. So I took this root x. Integrating is really kind of inconvenient, but the power on root is just a power of 1/2. And if it, sorry, go ahead. Or you're saying, well, this portion right here going down there. Oh, gotcha. What happens there as an exponent law is if you have a base a times a power, say, n, and the same base a times a power m, the powers must add. n plus m altogether.
Mhm.
So we took a power of 2 over 2 plus 1/2, add them together to get 3/2.
I got that, but I'm not sure where that X two over two came from.
That x, oh, this one right here.
Yeah,
That one started as x power 1, just a x. I wrote in power 1, and the reason for doing all that is I knew I had to add the exponents. So I took the 1 and wrote it as power of 2 over 2. Now I have the common denominator for the 1/2 right here. Adding them together is giving us what's the 3/2 in this location.
I didn't put X on the diagram, that's. what I-
Oh, gotcha, sorry. Yeah, so the x came from the r of x right here, and it dropped in.
Oh,
Other questions so far? Okay, well, let's take this. 2 pi times 2/5. We can leave that all just factored out in this format and evaluate x power 5/2 from 0 to 4. Now we're going to get our exact volume of, let's see, we can consolidate the constant, that's 4 pi over 5. Next, at x power 5/2, input a 4. It's now 4 to the power of 5/2. Minus, put in a value of 0. So here's 0 to the power 5/2. Nothing fancy happens there. But this one we can simplify a good deal. 4 to the power of 5/2. You can think of this as a square root of 4 to the power of 5. I usually go this route if I'm going to do it by hand. So the square root of 4 came from the 2 down here. Root of 4 just comes out as a 2. And 2 to the power 5 comes out as 32 altogether. So we're staring at a 32 in that location, and this turns into 4 pi over 5 multiplying 32, and so that's something like, oh geez, 128 pi fifths units cubed. You don't have to say units cubed, but that's just a reminder that what we found is a volume of this whole thing if we rotated it about the y-axis. So we did it, folks. That's our first volume problem done by cylindrical shells. A whole bunch of stuff happens under the background. There's infinitely many different cylindrical shells being constructed, volumes being calculated and being added up when we're doing this all together. Then we just kept adding more and more shells, taking the limit. So all that process we did turned into that complicated limit. Somehow, some way, that limit is exactly 128 pi fifths. The only way we really got that answer was fundamental theorem of calculus tells you you don't have to do that limit. You could just find an antiderivative right here and evaluate it in this way. So that's our process. So it's kind of a miracle in computation. This is a lot of crazy stuff happening all at once in this diagram. But any questions at all, folks, on the conclusion here? Okay, well, let's try this again. So usually these are kind of like a warm-up question, but I mentioned on the real final exam, we don't have a lot of opportunity to practice these problems. And so I'm going to pick essentially by random, using a real random number generator, either a problem out of 6.2 or a problem out of 6.3 that we're currently in. If you have the formulas ready for both and know how to read these kinds of diagrams, like these produced, then you'll be in really great shape on walking through the problem. It'll be a standard one where you don't have to do as much of this work in the middle, because again, the emphasis is more on just doing another integration problem that happens to be a volume application. So let's try this one out again on example 2. We're going to use cylindrical shells to find the volume of the volume. This one is generated by rotating the bounded region about the given axis. So first we need a region specified by y equals root x squared plus 1. Then the next curve is y equals 0. Next curve will be x equals 0. And the last curve, that's weird to say curves, they're straight line segments, it is x equals root 3. And we're going to rotate about the, let's see here, y-axis. Well, thank goodness, that's a type of thing you want to do for cylindrical shells, a y-axis rotation. So the way we'll start off this problem is, if it was a homework problem we were practicing, it's pretty good practice with just working with this kind of stuff. We're starting at y equals 0. That's going to be a horizontal line. Let me first put down a quick plot here. So when it says y equals 0, we're thinking the entire x-axis. X equals 0 is going to be the entire y-axis going this way. So we have some unusual bounds at the moment. I'll undo the highlighting, but that's just to convey those two bounds we see. Next is this function. Now, if you plug in x equals 0 inside this function, we'll have the square root of 1, which is going to come out to a height of 1. So at 0, we're right at 1. And next bound is root 3. Can use some scratch work for this. At x equals root 3, we get y equals root of root 3 squared plus 1, which will be the root of 3 plus 1, giving the root of 4, giving now 2. So at the square root of 3, let's just plot it here. We're at 2. So those are the two values so far. The curve for this one is not exactly a straight line segment. It has a bit of curvature to it. It looks about like this. So let's take a look again. We had x equals root 3, but that's a vertical line segment. It would have really come up and gone through here. I mean, it goes up infinitely and down infinitely, but it looks like this is the range we'd want to show it on. We're also bounded below in this region here, just another line to emphasize it. We're bounded to the left on this region, coming from the x equals 0, and this is the y equals 0. So we really do have a bounded region in the plane. We could find the area of this thing if we wanted to, but what we want to find is what happens if you rotate the whole thing about the y-axis. We're going to get some unusual looking solid if we do that. Well, we might be able to plot this one. Let me give it a try. I'll use a slightly off-color gray, just so we know what the right or the original diagram was. So over here at negative root 3, we'll have a value here. Symmetrically, something at this height. And it would look about like this. It is three-dimensional, so you'll also have an edge coming around here. And this is where my plots start to become kind of hard to read. So use your imagination. It looks something about like this altogether. That's kind of hard to visualize. If you can't draw the three-dimensional diagram, that's okay. The thing that would be provided on the exam is everything you see here in black. And it turns out that's enough to actually solve this whole problem. If this was a real final exam question, this would be probably the first thing I would do. The valid range for x is any value here to here on the darkened portion of diagram. Let's just plot something randomly here. Here's x. Once you place x, a vertical line is emerging, and this is going to turn into a cylindrical shell where this piece rotates. It rotates here to here. This would be a portion that we couldn't quite see. And here's our cylindrical shell. We need two things, the radius and the height. Let me remind myself on the color coding. So the radius on this one is going from the center all the way to where x is. But like we mentioned, I'm not going to ask for a weird axis to rotate about. We're always going to rotate about the y-axis for this problem, and that means the radius here is just x. So r of x is x. That's kind of nice. Next thing is the height. That's not so bad. When we say height, we're talking about that portion. This is h of x. And the height of this segment is whatever this curve happened to be. It's this one, root x squared plus 1. So we've got now a radius, we've got a height. That's all you need to now run through the whole problem. The formula goes like this to start us out. Volume will be a definite integral from a to b of 2 pi times a radius times a height. And we'll integrate this one with respect to x. So that's the start of the problem. First thing we need is that bounds of integration, where x could have been placed as far as way out here to 0, and as far to the right as up to root 3. So that means we're integrating from 0 to root 3 on this problem. Then we have 2 pi. Put in x for the radius. And then the root of x squared plus 1 for the height. So that's our format so far. And all we need to do is get through this integral. But this problem is now really a bona fide review problem for the final exam. This, just on its own, could be a real final exam question. And this one is a U substitution we have to get through. Well, that's our next thing, get through the U substitution on this. Any questions first, folks, before we start? Unfortunately, actually, yeah, you could put x inside there. Thanks for mentioning that. You could take, I write this as our x could be rewritten as root of x squared. And ordinarily that might have a problem, but x can only be positive. So we don't have to insert an extra negative sign. Here you'd have x squared plus 1. So you could put it together and get root x4 plus 1. But then the challenge with this is, I'm not too certain how to find the antiderivative of that function. This one could be certainly a big challenge, I'd say.
2 over 2 and then x squared plus 1 parentheses x to 1/2, or we call it 1/2 and then one side of the
Let me get to this step right here. You said put in a half here, dx.
Yeah,
And then what was the next step?
if we would do x is 2 over 2.
X is, you're saying this one has 2 over 2, the power, or?
The first x in the equation is 2 over 2, and then if we use x squared plus 1 power of 1/2, then we can apply that x into it.
So you're talking about this x.
Yeah.
Right, this x has 2 over 2.
Mm-hmm.
So 2 over 2 like that.
Right, to the power.
Oh, a power of 2 over 2. So if you go to a power of 2 over 2 like this, it still cannot get in. Well, yeah, that's kind of what we're doing right here.
Okay.
And then it turned into x squared times x squared plus 1 to x4 plus 1. But then we have to do this antiderivative right here. That's where the challenge certainly emerges at that location.
Okay. So could it be done with the chain?
Well, that's what we would have done over here. This one's going to be done by undoing the chain rule as well.
Oh.
But trying to do this one it looks like it'd be actually really quite hard. If I tried to guess one, I would say maybe the power goes up by 1. So it'd be the power of 3 over 2. And I know we'd have to invert to put in a 2/3, x4 plus 1. But if you differentiate all this, then it's going to turn into the chain rule. We multiply by the derivative of x power 4, which would be 4x cubed. So that means we probably need a 4 down below right here. And possibly, I can't just put x cubed below, because if I put x cubed below, if you differentiate that answer, it's now chain rule and a bunch of other rules altogether. Again, this one looks like a tough antiderivative in this format somehow.
So it could be possible, but it's a lot harder.
Yeah, this one is going to need some kind of ad hoc method to try to undo. Honestly, probably the best way to do this one is to unwind it, take out the x squared, and let your x emerge right here. As strange as it sounds, the thing that's kind of weird about our method is the cylindrical shells producing an x right here gives us a whole bunch of new problems that we couldn't have done before, but we can now do, because U substitution is effective at this step. But at this step, I'll leave this here on the notes. This one looks really challenging just all on its own. Challenging integral for sure. Other questions so far to this stage? Okay, those are the right kind of things to think about. Yeah, go ahead.
Like before, you still want to pull out the number 2 and 5?
Yeah, absolutely. I think that's always a great first step, because that way we're focusing on the portion of the problem that really is going to matter a lot, everything else. But you know what's kind of odd about this one is, if we did a U substitution, I bet you we would pick x squared plus 1. It's an inner function. Usually that's a good choice. The differential is going to involve a 2x. So you know what? This one time, 2 might be good to just leave alone right here. So let's leave the 2 in, but pull the pi out. Other questions so far? Okay, so I'll leave this method here. I didn't see anything by visual inspection to get through it, but if you find a way to get through this one as it's formatted as this problem, don't hesitate to throw it out there. It's always interesting to see different ways to resolve these kinds of problems. On this one here, let's pull out the pi. So it's going to be pi times an integral from 0 to √3 of x, or I still have a 2 there, 2x root x squared plus 1 dx. Now next I'm going to do something a little bit weird. I'm going to reset all of my color coding. Let's pretend this is a problem on its own. First thing we want is a good choice of u. And let's try x squared plus 1 and just see what that gets for us. Actually, let me make that green. We usually left our u as a green and the differential in blue. Not that it super matters, but if you get into a habit, it could be disconcerting to change that habit. So x squared plus 1 goes here. Next thing we want is its differential. There'll be a du equals, derivative of all that is just a 2x. And then we hit it with a dx. Now, after you pick a u and you calculate its differential, this is the moment of truth. You have to swap out everything in here that involves an x. So first thing I see is, well, we chose all that to be u, so we're in good shape with the square root. Now, the x dx along with the 2, so 2x and dx, that's going to convert to a du, so everything here is now accounted for. Only last things we probably worry about are changing those limits of integration, and we'll be in business. So let's make that last step happen. When x was √3 or x was 0, that's when we were doing a dx problem. It's now changing to a du in the integral, so that means we'll change the limits as well and write out u equals. We take the √3 and just plug it right inside here. You might use green for that. I think that makes a little bit more sense. U is going to be equal to √3 squared plus 1 going inside here. So this will be a 3 plus 1 altogether, giving us an upper limit of integration 4. Now let's do it again. And the lower limit, we're plugging in a 0. Well, that's a faster computation. We just get a lower limit of 1 in our brand new integral. So follow the yellow color coding. That's going to be our new limits of integration. I think we're just about all set up to finish off this one by u substitution. Any questions at the moment, folks, to that stage? Okay. And notice again, it's the same exact integral right here by the red dot. And this is what's tricky about integration. It's like you're trying to break some crazy combination. And if you change the functions, something that's approachable can look completely unapproachable just all of a sudden. That's very odd about integration. But now down here, here's what we're going to get. This is equal to pi still. Our lower limit of 0 is now 1. Upper limit is 4. In blue, 2x dx has converted to just a du. The square root next, we'll write in as a power 1/2, just to make integration much more friendly. And in green, x squared plus 1, this turned into just a u. And so that's our antiderivative. Now this one is hard, and I would say this one is even harder, but our methods are designed to take things that look unapproachable, bring it back down to section 5.3. This is now a fundamental theorem of calculus problem when we started those in 5.3. And what's even better, because we changed limits of integration, we don't even need to go back to the original variable u. In fact, we did when we changed the limits of integration. We already took care of plugging in the √3 inside there, getting that value out. So however you do the process, you really are doing the same exact steps. This method just happens to be slightly easier to write out. So let's find our antiderivative. Pi is a constant, just multiplying. U power 1/2, add 2/2, and you'll get u to the power 3/2. You might have noticed that's a very common antiderivative for some reason. There's lots of roots we do. Once you get that exponent, multiply by the reciprocal, so 2/3. And all this is evaluated from 1 to 4. Does that look right so far, folks, to that stage? Okay, let's do the evaluation next. we have 2 pi over 3 for all the constants in front. Right here, plug in 4, so now it's 4 to the power of 3 halves, minus 1 to the power of 3 halves. Let's do the 4 power as scratch work in the margin. 4 to the power of 3 halves becomes square root of 4 to power 3, so the root of 4 is 2. 2 power 3 comes out as an 8. So right down here on our problem, we're looking at 8 altogether. We've got a 2 pi thirds times 8 minus 1. So this is 2 pi over 3 times 7. Finally, we got our end answer of 14 pi thirds altogether. So this structure, the one in black here, around here, if you rotate about the entire y-axis, this is about a volume that it would take up. This one would be some kind of bowl, it looks like, and it wouldn't actually leak because there's no 1 point separation here. So some weird fruit bowl, I guess, is what we're printing out. Well, whatever it is, we found a volume, but the major takeaway of this problem is definitely this portion right here, where we reviewed the U substitution to finish it. Any questions at all, folks, on this one here? Okay, so 2 random volume problems are now done. The next one is going to be our application for volumes, but again, it's really just a disguised review type problem. So here's the scenario. It says a hill will be leveled. Imagine maybe you work for the city of Idaho Falls, and they don't do this very often. And so if they're going to level a hill, they're going to use the earth for something. It says the earth will be used in a land reclamation project that includes a construction of an additional landing strip for an existing airport. That could be Idaho Falls. That could be something they might do when they expand. It says the hill resembles the solid of revolution obtained by revolving the region under the graph of the function f, this function right here, on the domain from 0 to 240, so that's in feet going here, about the y-axis. So the claim is that this pile of dirt is extremely symmetrical. That's possibly a sketchy claim, but that's okay. The city of Idaho Falls moves this quantity of dirt every once in a while. They don't have to get it perfectly. But what they would want to know is an expectation of how much work is going to be done before they start paying for the bill. And so we're just doing like a back of the envelope computation of how much cubic feet of dirt are we really moving here in this land reclamation project. It says for our instructions, approximate the amount of earth that can be recovered using 6 approximating rectangles, taking sample points to be right endpoints. So in other words, we'll approximate the volume of this solid of revolution, the revolution being this rotation right here. Let's just say solid of rotation. I think that makes more sense. Solid of rotation using R6, the right endpoint rule with 6 subintervals. And counting them, we have 1, 2, 3, 4, 5, 6. This one is at height 0, so that looks like it's the right strategy. Any questions, folks, before we start this one off in earnest? Okay, probably what I would want to do first with this one is, let's suppose we were doing this whole problem as an example 2 problem. Let's write out the actual volume equation here, and that will help us get started. It's actually kind of a tricky problem because a lot of times when this type of question is asked and there's a rotation, it's tempting to just write down a formula that's giving the area here, not actually accounting for volume being the thing we want to calculate. But if we make this our first step, we won't make that mistake. The volume is rotated about the y-axis, so we're using the method of cylindrical shells. The limits of integration go from 0 all the way to 240. Inside is going to be 2 pi. The radius is just going to be x on this one, like we saw before on the other problems. So I'll put it in as just x. The height is going to be f of x. But we have oddly convenient height measurements all over the place. That's the purpose of all those numbers. If we didn't have those, that'd be okay. We would just eyeball it. I would have said, that looks like 140 maybe, if I was just looking at it without that information there. So whether these are here or not, we can still do a problem and get a reasonable estimate as an exam type question. Dx goes in right here. And like we mentioned before, if you can eliminate a constant, it's probably a good idea. So let's kick out 2 pi. It leaves 0 to 240, x f of x, dx. And just as a reminder, this, I guess that's tan curve is y equals f of x. So that's the thing we're going to approximate using R6. So the R6 estimation is all of this right here. We still have to multiply our end answer by 2 pi. Does that make sense so far, folks, with this strategy? Okay, since we're about to approximate using R6, let's write this in now as 2 pi times R6, and now start to convert to the methods for the right-hand rule with 6 rectangles. Next thing we need is delta x. Formula is always going to be b minus a divided by the number of approximated rectangles n. In this problem, we're using a finite number, so n turns into 6. In the numerator, you can use the integration or the diagram. The upper limit b is 240. And the lower limit is a, which is 0, or the 0 up here from the diagram. So delta x is 240 divided by 6. And you know what? After doing all that, that's kind of a silly thing to do. You could kind of just eyeball this. That's delta x right there. It should be 40, right? Well, at least we put down the formula. Some problems you do have to use that formula. So think of that as just completion on the notes. Delta x has to be 40 just per this diagram. So now that we have delta x, we have all the rest of the information we need. We can just start writing out the answer. The end answer on this one looks like this. It's going to be 2 pi times our delta x, so 40 goes in. And then next, we have to pay special attention to our integrand. The first value, x1, is going to be 40. It might not hurt to write those out. x1 is 40. x2 is 80. x3 is 120. x4 is 160. x5 is now 200. And the last one, x6, is 240. And my penmanship kind of went bad there. Let me fix some of those. So those are all the values we're going to put in. But notice if there's an x and f of x, on the first one, if x1 is 40, 40 goes here to start. And then 40 also goes into f of x, where we grab the value 146. So 40 times 146. And then we go down the line. Next, we use x2, which is at 80. 80 goes here for x, just because it's part of the integrand, just a consequence of cylindrical shells. Multiply that by the 104 right above. And once you have a couple down, with the aid of the diagram that's just kind of rinse and repeat as fast as your fingers can move, you can put in the next one. Look to here, plus 120. Then the height of the function at 120 is the 88, so times 88. Now we're over here, plus 160 times 44 plus 200 times, this one's hard to see, but it's 20. And there is still one more. It's going to be plus 240. They didn't say much on this diagram here, but we can interpret it as hitting the x-axis finally at this location. So times 0. The last term turns out to not have mattered with the right endpoint rule. So that's our description so far. All we need to do is throw that into the calculator and we'll be on our way in this problem. Any questions or comments, folks, at this stage? Okay, I did want to make one important comment about the exam. you will have access to a calculator, a nice like TI-30 X2S. And you could throw all that into the calculator, give me an approximation, that'd be terrific. But if you're short on time, I would say, don't do that. Solve the problem, get to this stage, and then go to solve everything else first. Come back to this one and give an approximation, just to check if your approximation seems to make sense on the diagram that you're looking at. So let's make this comment right here. I will, in fact, on a real final exam, accept this for full credit. This is accepted for full credit. You give me what's about to go into the calculator. Even if you did make a mistake in the calculator, I would attribute that to, well, I can have fat fingers on a calculator and hit a plus when I hit minus. I would just say it's a simple mistake. If I see this, you know the calculus, I would give all the credit for that description right here. Still, it's a good idea to finish it off if you have time in an exam setting, just to see how reasonable your answer is. Does that make sense so far? Okay, so if you see a long string of numbers that looks like it's going to be really tedious to put in the calculator, just write it out. That's full credit right here. But let's see what we're going to get here out of this one. Plugging all this into the calculator is not too bad. We're going to get 2 pi times 40 times 146 plus 80 times 104 plus 120 times 88. It feels more tedious than I thought it would be. 160 times 44 plus 200 times 20 plus 240 times 0. We could have neglected that term. And this is our result. It's 8,987,468.3 cubic feet of dirt. You know, probably a better way to write this answer is just scientific notation at this point. Let's call this 8.987 times 10 to the power of, let me double check. I think that was 1, 2, 3, 4, 5, 6, 10 to the power of 6. So that's how much cubic feet of dirt would have to be moved. But we did it, folks. If you're working for the city of Idaho Falls and they're doing this project, here's the back of the envelope calculation to tell them a reasonable expectation. Then they might get some people with interesting topography, mapping, things like that to give a better estimate. But this would be a good first pass. The city might say, well, that's way too much or reasonable, and move the project forward after that step. Well, any questions at all, folks, on the end of these notes here? Okay, well, congratulations, everyone. This is all of the topics of the course so far. What we're doing next is just converting over to reviewing for the final exam. So let me save up these notes. Takes a moment, there it goes. And the document we're going to very next is going to be this one right here, the one called review. I want to save the original final exams that were given in the past for your own personal study. That way, they won't feel like they're problems that were kind of been done and redone a whole bunch of times. So these problems over here are all fresh problems. Some of these were written by me. Some of these were written by other members of the department. Yeah, go ahead.
Related to the problem I was asking about.
Oh, yeah.
I tried it the way I was thinking, and it comes close, but it's not right.
Oh, gotcha, yeah.
So I got 3 square root 3 pi instead of 14 pi with 3, so it came close to that.
It did come close, yeah, that's interesting. Other questions so far? Okay, well, our first problem of the day is really just one massive review problem of taking different limits. Let me see if I can zoom in here a little bit better. We have the graph of a function y equals f of x. It's got all sorts of issues. It has lots of vertical asymptotes, lots of jump discontinuities, and all sorts of things going on. What we're trying to do here is not trying to estimate each limit precisely, but we're going to look at each limit or just statement like this one and determine if the specified quantity is positive, negative, 0, or undefined. So let's give this a try. We'll go right to left, top to bottom, starting on this one. X is going to head towards x1, from the right on the function f of x. So that means we're right here on this one. And the visualization is we're just following this curve this way. We're coming in from the right, we move down in this way. We get closer and closer to x1, and we have to put in what is the height itself getting closer and closer to. This one would be 0. You can get as close to 0 as you want by getting as close to x1 as we like. Does that make sense, folks, on that first one down? Okay, now let's give this another try. This one, we're heading to x2 from the right. So that means we're looking around x2. We also have to be careful with that directionality. Recall we're only going for 3 different types of answers. What would you all say for this one? Positive, negative, 0, or undefined? I agree, this one ought to be positive. Because of from the right specified here, we're coming in this way. We're going as close as we want to this number here, or this value or height. And all I can say for sure is that's positive. There's no values on the y-axis. Yeah, go ahead. Well, that's one thing that's one thing that's kind of nasty about this one. That dot on the x-axis tells us that f of x2 is whatever that value comes out as. I'll just write here is negative, so less than 0. But if it's asking for a limit, we actually don't get to plug in the x2 value. So we're always away from x2, and we're wondering what's the height we're going towards, getting closer and closer to. So this one comes out as positive, but good call as well. The function value due to that dot itself is this negative value, less than 0. Does that make sense about that question there? Awesome, thanks for asking that one. That's one thing that's nasty about these diagrams. We have to be really good at the open circles, the solid dots, and what that information is conveying as well. So that's 2 down so far. Now this one's a little bit weird. F of x2 minus f of x3. Well, now we really need this value here. That's the height of f of x2. This one would be the value of f of x3. They're both negative, but if you subtract this value from this value, x2 is larger than this one, you will get a positive quantity each and every time. In other words, the negative f of f3 takes this one and makes it the larger value altogether. Does that make sense to folks on this one being positive? Okay, I'd say this problem is kind of tricky sometimes. It might not be a bad idea to throw in a value like a -5, -3, and certainly -3 minus -5 becomes a +2. It has to be positive altogether. So positive on this one. I'm not sure where to put the answer on it. Let me see if I can fit it there. And now, next question is not a function, it's not a limit. We're wondering about the derivative of f at x4. So we go to x4, and I can certainly say that f at x4 is 0, but we need to be cautious. That's not what they're asking for. They're asking for the derivative of f at x4. Anyone see what this one should be? Good call. This one's got to be negative because at x4, the slope itself is negative. The tangent line is the line itself because it's linear. Because the slope is negative here, we'll come down and say the derivative of f at x4 is the slope of the tangent line, definitely negative. Actually, let's convey it this way, just to tie that idea together. If you always think about the derivative as giving you the slope, then you're in really good shape. That's the geometry behind this weird, crazy process here. That makes sense so far, folks, on that one? Yeah, absolutely. When it says f prime at x4, the way to think about this one is f prime at x4 is the slope of the tangent line at x4, f of x4. So when we go to that point, we're right over here. The slope is negative, so that means the derivative itself also has to be negative. Another way to think about it also is, think about back in the day, we did the increasing decreasing test. It said If your function is decreasing, the derivative is negative. If your function is increasing, over here, the derivative is positive. So that's another different way to look at the same kind of information. Does that help with that question there? Awesome. Other questions at the moment? Okay, well, we're on row 2. I feel like every one of these has weird, interesting topics worthy of review. So I believe this was Professor Dr. Lacour that wrote this problem out. I think it's an absolute excellent problem. So, oh, I didn't need to get rid of that one. I do want to get rid of some of these so the document doesn't get too busy. But I want to leave the one talking about the slope since this is always a good and important reminder. Now, we're doing the limit again. X is heading towards x3. Notice there's no pluses or minuses on this one. This one's a double-sided limit, and the limit has to be the same. Anyone see what this one should be?
Okay.
Exactly. For doing a double-sided limit, then you have to come from above and approach a value. Here we're getting really close to whatever that height is. But you also have to approach from below, and you must be getting about the same value as you get closer and closer to the x3 x-coordinate. Yep, in either case, we have positive values. So the limit also exists, and it's positive itself. If there was some other weird curve here, let's suppose the curve did this instead, and none of it was there, this limit would not have existed because we would have been approaching one height from the left, some other height from the right, we would have said does not exist instead in that case. So watch out for jump discontinuities. If there's a jump, the only limits that exist are the single-sided limits themselves. So let's now go to, that's an oddball question, x4. You know, I think the thought with this question was, these problems are confusing. And if you just put x4, we need to know we mean that one, so it's bigger than 0. I think this one is literally here just to see what we'll do with it, see if it throws us off or not, but x4 has to be a positive quantity. Weird question there. Let's move over to the not as weird one, the derivative of f at x6. Anyone see the value for that one? Good call. When you see the derivative symbol, think tangent line needs to be brought down on x6. And my tangent line, if I were to draw it freehand, would look about like that. It suggests a slope of 0, and so this one is definitely 0 here. That makes sense so far? Okay, that means this one looks kind of nasty, but question first, sorry. Oh, that's a great question on this one. Because it just said x4 itself, we're thinking about the number right here, x4. But I think what you're thinking of is, if it said f of x4, now it's talking about a function value, and we're talking about that value on the y-axis. So that one would come out as a 0. Again, it's kind of a tricky question. I would never ask these weird questions on a real exam. I think the only reason this is thrown on here is to compare it against, I really don't know. Maybe this one right here, the difference between putting in a value versus a function value.
Would you put this type of question on the final exam? Because we haven't seen this before, so in this setup, so this is interesting.
Really, this kind of question, really it's a review in the sense of we're reviewing just small parts. I wouldn't add this entire question with, 12 different parts on the exam, no.
I mean, in this format. Okay.
Or how do you mean, sorry?
It's different than what we've gone through in the first section.
Gotcha.
On how the layout is.
Oh yeah, this one wasn't even written by me. This one was written by a different person as well, yeah. So yeah, I'm gonna be writing down the questions that we're used to seeing, for sure. I wouldn't try to throw in anything too hard like this one. Other questions or comments so far? Okay, well, we've got derivative 0 on this one. And now this one is really very interesting. Second derivative, we're looking at x6 on that one. Let's clear out the document here. We need to decide, is the derivative or second derivative here at x6 positive or negative? It's a tough question in a certain sense, but here's the reminder on this one. Part H is a concavity question. The related question here is, at x6, are we concave up or are we concave down? Concavity questions are also tricky. If you're thinking concavity, what helps your eyes is lots of tangent lines. So let's go and convert this over to this view. I would probably still put the horizontal tangent line. There's a few more. And observe the curve itself is always going to be above those tangent lines around x6, however you draw them. Should I say again? Not concave down on this one, it'll be concave up, yeah. So if your curve is above the tangents, that's the concave up on this one. But yeah, this is definitely, like you were mentioning, a really oddball question. I wouldn't ask this one on the real file, but its purpose is just to remind us of all those weird little concepts. And it's amazing how they all can be brought into a graph in some way, shape, or form. So we'll say here, let's give a lot of explanation on this one. It's bigger than 0 since f is concave up around x6. So that's our concavity test coming really out of nowhere on this part H right here. Does that make sense so far, folks, on that part H? Okay, I think that one is kind of the nastiest one on the whole document because it's just surprising concavity could come up here. But now let's go to f of 0. Let me reset some of this stuff. So f at 0, any volunteers for what the value should be here? Absolutely. If we're doing f of 0, I mean, this document or this problem kind of makes us question things, right? But this is an ordinary function evaluation. F at 0 is this height. And so definitely it's bigger than 0 here. I think part F and part I were kind of meant to be two questions that were motivated in the same kind of thought, where one's a function value, one's just the input. All right, let's go to a more comfortable question next. Ordinary limit on this one. I never thought an ordinary limit would be a comfort, but here we are. X is heading towards x6. We need to know the value. Well, the limit doesn't absolutely exist. There's no jump discontinuity or any other weird features. And, you know, it's continuous here as well. The actual limit is equal to f of x6. That's continuity on this one. And f at x6 is less than 0, definitely negative. You didn't have to put it in this right here, but it's just a reminder. If you have continuity, you also have direct substitution. x6 goes right in here through continuity. So continuity is in a certain sense also on here in a kind of a forced way, to be completely honest. But now let's take a look at this one. We're taking a limit as x goes off to infinity of the function f of x. That means we're looking at this end of the diagram. Looks like there's an interpretation of a horizontal asymptote. The height would be at 0. And so that means this limit, as x goes off to infinity, must also be right at 0. Does that make sense to folks on that limit there? Awesome. And it looks like we have just one more to go. And it has to do with a derivative heading to x5 from the left. The last problem is always kind of a weird one. So let's see what's going on here. We're heading towards x5. We're only coming in through this portion right here, nowhere else. But the limit is relative to the derivative of f. Any volunteers for what we should get on this one? Let me think about that. Positive or 0. Well, as we head there, let's suppose we just took one value right here. We're supposed to head towards x5 from the left, but right here, oh, gotcha. Right at this location, the derivative would be negative. Does that make sense to folks? Only because we're on a straight line segment. If we draw a tangent line, that segment is the tangent line, and it would have a negative slope. Get closer to x5, it's still negative. Doesn't matter how close you get to x5, you just have to for sure stay to the left because it's undefined right at x5. But yeah, it looks like all these values in the limit are negative, so we're getting a negative value as well altogether. that make sense to folks on that last part L there? Okay, this one is kind of an oddball one. I kind of liked part H. It's a good reminder of what continuity looks like visually at a concavity test. And there was other interesting kind of problems inside here. But we did it, folks. That's our review of that problem. Any questions at all before we turn to a new one? Okay, well, example 2, I think, is kind of a hard one. We're plotting a derivative, and we've only got about 7 minutes left. How about we come back to this one where we're a little bit more fresh on Thursday? Let's pick out a different problem. So let's pick a round and see what would be a good for last 7 minutes. This one's technical, and I think I did say at some point in the class, something like this we should expect in the actual final exam. This might be a good one for us to end the day on. Let's see what happens with example 3. First one is about continuity. And continuity at 2, as a reminder, this looks like this. It's a direct substitution. So let's write this one out. We need to convey this information in the form of a limit, and it would be the limit as x tends towards 2 of the function f of x itself would just be equal to f at 2. So that's what continuity looks like as a limit. It means you're taking the value that x is tending towards, directly substituting inside the function to get an f of 2. Looking at a graph, it just means the graph is unbroken. You can draw it without ever lifting up your pen. So as a limit, that's what we're dealing with. Next one is a different kind of limit. And this one, you might first look at this in your notes. I would say this is something I would definitely include on my page of notes for the final exam, that f prime of x, by the definition of the derivative, is the limit as h goes to 0, f at x plus h, minus f of x, all over h. So if we're going to try to write this information down in the form of a limit, we'll first focus on that region, f prime at 5. That's going to be replaced right here. And we'll say this is the limit as h itself goes to 0 of f of something minus f of something. And the first thing that's going in there is this 5. It's going to be a 5 plus h minus f of 5. So what we've done is, where there was an x, if we plug a 5 in there, 5 goes into this position as well as into this position where the x's were. Then the whole thing is divided by h. Now we go to the right-hand side and just set this equal to negative 2. The right-hand side is not super special. That's just the right-hand end of the equation. The left end is where essentially almost all the partial credit would be. This would be like a half a point right here. Yes, go ahead. Or which portion right here? Oh, yeah. I'm not too sure where that negative came from. Thanks for spotting that. That should have just been 5 itself. Let me fix that right here. Just 5 matching that 5. Thanks again for spotting that one. It's kind of funny. You pointed it out to me, but it takes me a minute to find my own mistake. It's a weird thing about math, I guess. Other questions so far, folks? Okay, so these problems are kind of tricky in the sense that if I was to grade this one, definitely has to be a positive 5 here. It has to be a negative. We have to go 5 plus h. There's got to be an h there. And another thing, this one is the easiest one to miss, in my opinion. The limit has to be about h going to 0 as well. So it's unfortunate that this is so notationally dense, but every little bit there is truly important in this limit. The limit is relative to the h value. Well, let's try one more. And for this one, I do have the solution for this part C as written, but if folks don't mind, I would want to change the problem just a little bit. I feel like that one is not a great question. The way I would probably really write this question would look like this. Let's just say part C, alternate. We'll take something more like -3 to 7 of maybe root x cubed minus 1 dx. I would want to fill in the upper and lower limit of integration, give our actual true function, so a definite example rather than something abstract like this one. So let's work on this problem. Is that all right with folks? Okay, so if we're conforming this or rewriting this into the form of a limit, first step you might take is it's the limit as now this time n is going to infinity, not x, not h, but the value of n now. N is the number of approximating rectangles in this thing, the Riemann sum. We have index I going up to the last rectangle n. Summation symbol just says add things up. And the summation is just another way to view the integral sign, which is elongated s. Then we're going to take root xi cubed minus 1 delta x. So that's our start on this problem. And I would give a pretty good amount of partial credit right to this stage. But just like in the homework, there's a little bit more we've got to do. We need to find what is xi for this problem and what is delta x in this problem and fill in that remaining information like we did in the homework. So let me copy in lim. And heading off to infinitely many approximating rectangles, we're adding all n of them together. And let's leave this blank for the moment and find out first, what is xi cubed? Well, really good way to get xi is to start with actually delta x. The last thing in there is probably the better start. Delta x goes b minus a over n. And this time, because we're taking the limit as n goes to infinity, n stays exactly where it is. We're not going to change it out. But our upper limit b is the 7 from here, minus the lower limit below, -3. And I said 7, but I didn't write it. Let me try again. So 7 minus -3 will give us 10 over n. So now we know what goes there. But the reason we start at delta x is we now change to a formula for xi itself. Xi is a plus the index I times delta x. So filling in that information, we're going to get a is the lower limit of integration, -3, plus I times, just substitute in 10 over n. And you can bring it in exactly like this, but usually I simplify it just a tad. -3 plus 10i over n makes it just slightly smaller when we go to plug it in up here. So now that's all the moving parts. Take the delta x, your xi formula, and just substitute it in that information here. The Riemann sum goes square root of, for xi, it's -3 plus 10i over n, and then -1. Notice this does simplify. It'd be -4 plus 10i over n. But I would say for an exam kind of setting, an exam question, this one is not expected to be simplified much. You could leave it like that. Yeah, go ahead.
To cube that.
Oh yeah, absolutely. Yeah, so from here to here, we've got to raise it to power 3 as well. Thanks for spotting that. I was about to forget it. I was thinking about the negatives combining more than anything.
It doesn't include the negative.
Oh, it does not. I was about to make a bona fide mistake there. Thanks for spotting that. So with the help from the class, thanks Joey and thanks Summer, this should have been like this. It does not simplify. This portion to power 3, I think next -1. Definitely dropping the ball on that one. Thanks for the support on this problem here, folks. Does that look better as written? Awesome. So with the substitution done correctly, we're looking at that. Then last thing, delta x is times 10 over n. So we got it, folks. This one was a team effort, but that looks like the right bona fide answer. Let me circle this here to here, just for that extra emphasis on where the power should have gone. Well, any questions, folks, on the conclusion for this one? Oh, we ran right over on this one. Sorry about that. Well, we did it, folks. That's the end of the class today. When we come back, I think it's a good idea for us to still take a look at this example too. But then from then out, we'll try to cherry pick some problems that look like they'd be pretty good candidates of real final exam problems to get extra practice. You're also welcome to bring in any questions you'd like to discuss to start us out, and that'd be a great way to start. Well, have a great night, folks. Sorry for keeping you a few minutes after. And we'll come back on Thursday to finish off some more review topics. Another thing I forgot to mention, but I'll make another announcement. I do intend on having office hours on Monday. I'll be on the campus somewhere, probably my office, maybe this room if it's available, right around, say, about 11 o'clock to 2 o'clock before my first exam. So if you have questions, come down, send emails. I'll be available to help out.